In this video, we will discuss some of the Lissajous figures that arises in case of a coupled oscillator, which is consisting of a spring horizontally placed and another spring vertically placed and attached to this mass. So in that case, the displacement due to the horizontal spring is x and the displacement due to vertical spring is y. And here is a special case if the angular frequency of these two oscillators independently are omega 1 and omega 2. In that case, these two displacements x and y would follow the equation which is as depicted here. Now on the left side here we have shown the movement of this mass under the influence of these two coupled oscillators. So in this case, what you see is this red circle is moving on this horizontal axis and this big circle is moving on the vertical axis. So these are like harmonic oscillators independent of each other. So this, it's like here, if the mass is only attached to the vertical spring, then the movement of this mass would be represented by the movement of this blue dot, and if the mass is attached to the horizontal spring only, then its movement would be depicted by this red dot in the horizontal direction. Now what you see here is this pink dot represents the resultant motion of the oscillation as it is coupled simultaneously to these two oscillators, and in this case the phase difference between the two oscillations, the blue one and the red one, is given by 90, and the angular frequency for the two oscillations are same and also the amplitude are same. So what the circle is showing that when the phase difference is 90, then this particle or this mass under this coupled oscillator scenario would move in a circular fashion. So this is a Lissajous figure for the case of a coupled oscillator where the frequency is same and the phase difference between the two independent oscillators is 90 degrees. Next, what we are going to look at is, here there are multiple scenarios when we have kept this angular frequency of the two oscillators is like the two springs are not same now and one is heavier than the other, so their angular frequency is different. And in this case, the first one is showing when the phase difference is 0, and in this case the resultant motion is through such a closed curve and it would continue to oscillate along this closed path. So this is the resultant movement of the mass. Similarly, in this case the phase difference is 45 degree, then the path is not closed and the resultant path of this oscillator, coupled oscillator, is showing like this. Similarly, when the phase difference is 90, then this is the resultant path, and when the phase difference is 135 or 3 pi by 4, the path is like this. Now remember, here in all cases the angular frequency is 1 for the horizontal oscillator and half for the vertical oscillator. So it's like the vertical oscillator is little slow compared to the horizontal oscillator. Then in the next case, now the two oscillators have the same angular frequency. Again, for the phase difference of 0, the oscillation results into a resultant path of the oscillator to be in a straight line with an angle 45 degree with the horizontal axis. Then in the second case, when the phase difference is pi by 4, then you have the resultant path to be an ellipse, and then in case of the phase difference to be 90 degree, then the resultant path is a circle, and then in case of phase difference to be 3 pi by 4, in that case it's again an ellipse. So the difference between these two cases is that in both cases it's an ellipse, but the ellipse is slanted in different quadrants. Next, we have the angular frequencies are again not same. So when the phase difference between the two oscillations is 0, and then you have a very complicated Lissajous figure, means the path of the mass is like this. Similarly, for the case of phase difference to be pi by 4 and angular frequency is 1 and 1.5, the Lissajous figure looks like this. And similarly, this is another case of phase difference to be equal to 90 degree, and this is the case when the phase difference is to be 135 degrees. Next, here the angular frequency is again not same, and one is 2 times faster than the other. So here you have the oscillations are forming this kind of a Lissajous figure. So these are the different Lissajous figures for the corresponding phase differences. So these are very interesting curves. Now in the next case we have much more interesting Lissajous figures. So these are again for these different phase differences, and here the angular frequency is such that one is like 2.5 times than the other. So here the curve is closed. In these two cases, here the curve is not closed. Then we have one more way to look at this Lissajous figure is, so earlier what we have shown is we have placed omega 1 and omega 2 to be some values, and then we showed if you change the phase, then how that changes the resultant path or the Lissajous figure for this coupled oscillator. So next what we will see is that if we change these angular frequencies and keep the phase difference to be same, in that case how the Lissajous figure changes. So what you will see is the resultant Lissajous figure, and for each different combination of omega 1 and omega 2, the Lissajous figure will change. So here it goes. So for each different values of these omega 1 and omega 2, the Lissajous figure means the resultant complete path of the coupled oscillator of the mass is changing in this way. For example, if the angular frequencies are such that it's 3.01 and 1.00, in this case the Lissajous figure is not closed and it looks like this. Similarly, this is the Lissajous figure for angular frequencies to be equal to 1.47 and 1. The phase difference is 0. So here it's again will iterate the different values of omega 1 and omega 2, keeping the phase difference to be pi by 4. So these are the different Lissajous figures for different phase differences, and as the difference between the angular frequency changes, the Lissajous figure also changes. So next, so here we have shown you if we fix the phase difference to be 0, pi by 4, next we have pi by 2 and 3 pi by 4. So here are the Lissajous figures as the angular frequency is changing. For example, these are some Lissajous figures. So in this case it's 1.9 and 1. So this is the Lissajous figure. So this figure starts from here and then continuously moves, and this is where it ends. And similarly in this case, so as the frequencies are changing, the Lissajous figure is also changing. Next, this is our last case. In here the coupled oscillator has a phase difference of pi, and as the angular frequency is changed, that's how the Lissajous figure is changing. So these are some of the interesting Lissajous figures that you can see in case of a coupled oscillator consisting of two oscillators. Thank you very much.